Okay, we're going to finish section 9.2 today. We talked about multi-stage experiments last time a little bit. We had taken a look at the fact that we're going to do tree diagrams or something like them for each of our problems, and we had done one example right here where these were not independent, they were independent events, but the category numbers changed every time because we were not replacing the people in the basket, right? So all the numbers were different in all the branches. Not all of our branches are going to look like that, but on this one that they did. So we're going to do an example next that's going to be a variation of a tree diagram. You can do a tree diagram for this. Let me just say that right now. There's nothing wrong with that. But there are a couple other things you could probably do that make sense with this as well. And so I'd like to show you one of them. So we've got a box and it contains 5 slips of paper. 4, 6, 7, 8, and 9. The player reaches into the box and draws out 2 slips of paper and adds them together. If the sum's even, the player wins. If it's odd, they lose. Okay, so can you picture what's happening? So they can't reach in and grab 2 7s, right? Because they're reaching in and grabbing 2 of them at the same time. They're not putting them back inside and grabbing it again. Okay, so they're grabbing 2 separate numbers. They're going to take whatever those numbers are and they're going to add them together. So what we're going to do is we're going to actually write out all the different things that they could pick, okay? So when they reach in, they could pick a 4, and we'll just kind of go in order, and a 6, right? And I'm just going to write it as 4 plus 6 for the moment. We'll write the totals out in a second, at least I will. But if they don't do a 4 and a 6, they could do a 4 and a 7, or they could do a 4 and a 8, or they could do a 4 and a 9. And these are all the ways that they could pick a 4 with something else. Okay? So I don't need to write down the 4 ever again because I've listed every possibility that includes a 4. Okay, we're going to do the same thing again with the next number. So a 6. Yes, there's a 6 and a 4, but it's already on my screen, so I don't list it again. But I could do a 6 and a 7, or a 6 and a 8, or 6 and 9. Okay, what would be next? Okay, so 7 and 8, 7 and 9. And what's my last one missing? 8 and 9. Okay, so let's go through and find all these sums, and I'll just write them in a different color to draw our attention to it. Let's do blue. All right, so this one's 10. I have 11, 12, and 13. I have another 13, a 15, and, a 14 and a 15. Get carried away. 14 and 15, and then this one is 15 and 16. Did I get those all added right? Okay, so we have listed out every single outcome, and every outcome is equally likely because it's a randomized picking 2 numbers out. There's not like one of them is heavier paper, so you're more likely to pick it, or like crumpled or something. Like there's no edge. No number has an edge on another number. So we'd like to go through and just figure out how many of them actually allow us to win. What does it take for the player to win this game? Has to be even. Yeah. So 10's even. What else? 12. Okay. Did I get them all? So how many evens are there? 4. How many possible outcomes are there? There are 10. And if I reduce that, what's the probability? 2 over 5, right? 2/5 probability. Part B says, what happens if we change this so that the numbers are multiplied? Would it change the probability? Well, it seems possible that it would anyway, right? We have to check and see. The answer to being yes or to being no really does depend on the numbers that are in that basket and how they're arranged. I'm going to erase all of the sum values that I got because I don't want it to confuse us for the next part. And we're going to think about it as multiplication, and you're welcome to multiply them all out if you wish, but you don't really have to. The reason you don't really have to multiply them out is because if you were to multiply these things, and you're trying to just see if you get an even, how can you know without actually doing multiplication if a product is going to be even?
If there's an even number, it's automatically.
You got it. If one of the factors is even, it's automatically even. Did you know that? Okay. So if you multiply a number by anything that's even, you automatically get an even result. So I don't have to actually write them all down, but if you want to, you can, right? But this one's an even, because there's a 4, this one's a 4, this one's a 4, they all got 4s. So all of those are going to be even. 6 is also even, so everything that includes a 6 is even. 8 is even, so everything that includes an 8 is even. In fact, the only one that's not is the one that has the 7 and the 9, right? So if I did this same experiment or game, and I wanted to know if multiplication changes things, does it? Yeah, the probability is different. So does it change? The answer is yes. And if so, what does it change to? So what's the likelihood of winning if the outcome is multiplied instead of being added? Yep, it's a 9 out of 10 probability. Okay, does that make sense? Are you sure, Allie? Are you good? Okay, just checking. All right, let's take a look at another one. And we're again going to do it with a slightly different, like a variation on a tree diagram, because I want you to see some other options. I've got some more tree diagrams coming later, fear not. So the next one actually is an experiment that consists of first spinning a spinner, spinning with spinner number 1, and then spinning spinner number 2, okay? And I think it's fairly believable, and it should be true because I tried to create it to be such that the sections in these spinners are evenly divided, right? There's exactly 2 evenly divided sections in spinner A, if you will, and there's exactly 3 evenly divided sections in spinner B. Does that make sense? Okay, so I'm not trying to optical illusion you on anything here. That's not the goal here, all right? Okay, so it says first, it wants us to write a sample space for the experiment. So sample space means to list all the outcomes. And because these are evenly divided, all the outcomes are equally likely. Like if I spin spinner number 1, you have a 50-50 chance, like a 1/2 probability of getting a 1 and a 1/2 probability of getting a 2, right? Exactly the same. Same thing for the spinner 1, 2, 3. You have a 1/3 chance of getting each one of these. So you're equally likely to get all of those outcomes. So in my sample space, we write those curly braces. And I kind of like to write them in an ordered pair notation. You don't necessarily have to do that. You could just list the numbers. Like I could just say, okay, I could get a 1 and I could get a 1. That's fine. I tend to do this with my notations because I think it sort of doesn't confuse me that I just wrote down the number 11 or something like that. So I could get a 1 and a 1, or I could spin a 1 on the first spinner and a 2, or a 1 on spinner 1 and a 3. Or I could spin a 2 on spinner 1 and a 1, a 2 on spinner 1 and a 2 on 2, or a 2 and a 3. So there are 6 outcomes possible from my spins. Does that make sense? Now it asked me to do the sample space diagram, so this makes sense to actually write this down. I mean, like it's requested. And this is sufficient. I don't need a tree diagram for this. Why? Because each of them is equally likely. Okay? So we're going to take a look at some questions that are asked then. It wants to know the probability of spinning 2 even numbers. So where do you see 2 even numbers listed here? 2, 2. And it's the only one, right, Catherine? Yeah, it's the only one of them. So there's one way of getting 2 even numbers. Out of how many different possible outcomes were there? 6. So you have a 1 out of 6 chance of getting a 2 and then a 2. Notice it's the same thing as multiplying the probability of getting the number 2, which is 1/2, times the probability of getting the number 2 over here, which is 1/3. 1/2 times 1/3 is 1/6. Okay, so everything agrees. It's not a different approach. They give you the same answer. How about spinning at least 1, 2? Okay, well, that's a little bit more, cumbersome to find them. It's not bad. But do you see all the outcomes that would include at least 1, 2? So this one, and this one, and this one, and this one. There's 4 of them, right? 4 of them have at least 1, 2. Out of how many total? 6. And what is 4 out of 6 if I reduce? 2/3. Good deal. What is it going to do when it wants me to find exactly 1, 2? What's going to happen differently?
You have to take the 2, 2 out.
Yep, this one right here does no longer get included. I'm going to try and get it to delete. Because it had 2 2s and it's supposed to have exactly 1, 2. So if I remove, sort of that in my counting, how many do I have? 3 out of 6, which is 1/2. Okay, All good? All right. So this question was written ages ago when Eli, my 17-year-old son, was about 5. Okay, I'm pretty sure none of these it was made up then anyway. But this was the background of this question. When I purchase a new shirt for my son, try that again. There is a 0.15, right, 1/1500th probability that he will stain it the first time he wears the shirt. If the shirt is stained, there is a 2/10 probability that I will not be able to adequately remove the stain, right? It is stained forever. That's what it's saying. So then, what is the probability that my son's new shirt will be permanently stained after the first time he wears it? Okay, so one of the reasons this is in here is not just because it's kind of cute and funny, but because I want to show you that sometimes your tree diagrams are not balanced. Okay, so this is a really good example of that kind of a problem. So there's 2 things that can happen when my son wears the shirt for the first time. What are they? It's stained or it's not stained, right? So we get it to be a stain or no stain. Okay, so if it's stained, then I have to scrub it and try to get the stain out, right? But what if it's not stained? Then I don't have to do that. So I only need to extend branches off of the stained category because I don't have to do anything special if the shirt is not stained. Does that make sense? Okay, so you're going to have some defective and non-defective items, something like that in your question sets. And they follow this kind of a pattern, right? If it's not defective, it's good to go. You ship it off to whoever's going to buy it, right? If it is defective, you either got to fix it or something else later, something like that, right? Okay, so stained shirts get treated. What are 2 possible outcomes when I treat the stained shirt? It comes out or it doesn't. Stained forever. Those are my outcomes. All right. What is the likelihood that when my son wears the shirt the first time that he stains it? You find it? Yeah. And another reason that this is given to you this way is because I want you to see we can use decimals. There's nothing special about fractions, though we've seen fractions used on many of them. So if it's got a 0.15 chance of being stained, what is the likelihood that it's not stained? What is it? 8.5. Yeah, you're getting close. 8.5. So how did you get 8.5, Miranda?
100 minus 15 is 85.
Yeah, we're trying to get every pair of branches, to add to a 1, right? So I need these 2 numbers, whatever they are, to add to 1. That's why it's going to be 0.85. Cool? Okay, now, if it's not stained, then we just put it in the wash and we're done. But if it is stained, now we go to our top set of branches. What's the likelihood that the stain, which one did they give us? They gave us, or I gave us, 0.2 probability I will not be adequately able to remove the stain, so that one goes down here, right? Stained forever. So what's the likelihood then that we can get the stain to come out? Yeah, it's 0.8. Again, because those 2 numbers add up to 1. Okay. And then we learned about the multiplication property for tree diagrams last time that says that if we want to find the outcome along any branch, we just multiply the products along those branches together. So this question says, what's the likelihood that it'll be permanently stained, that's right here, stained forever, after the first time he wears it? Well, we got to follow along that branch. So we're going to end up multiplying the 0.15 and the 0.2 together. Carefully through decimals if you're doing it by hand, or even if your calculator, just entry and so forth. What will this give you? Anybody have it? Thank you, Brooke. 0.03. That's like 3%. 3% chance, which cannot possibly be true. I mean, like in real life for my son from when he was that age, because he stained things a lot. But that's good. So it's 0.3 for 0.03 for this one. Good? Okay. The last 2 examples are both going to have tree diagrams that are more balanced than this, okay? So the first one we're going to do here is I'm going to talk about Joe. Joe says that if a family, has 2 children, then the only possibilities are 2 boys, two girls, or one of each. So let's just pause right there and recognize that is correct. Okay, so we're not going to fault Joe yet. We want to see what he says next. Because there are only three possibilities, which we agreed that there were, the probability of having two boys is 1/3. Is Joe correct? Okay, so the answer is Joe's not correct. And I'd like to come over here to remind you what I said over here. These were our 6 outcomes. And we could write them like this because they were all equally likely, right? All right, 50-50 shot in the first spinner, 33-33-33 on the second spinner, all equally likely. The problem is that these outcomes are not all equally likely. So let's draw a tree diagram so you can see why. Okay, so Joe's wife has baby number 1, and the 2 outcomes for baby number 1 are boy, girl. What's the likelihood she has a boy? Yeah, 50%. So Phil, let's just do decimals on this one. We'll do fractions on my next one just so that we kind of are varying it. So it's a 50% chance boy, 50% chance girl. Everybody good with that? Okay. And then they go and they have child number 2. So we do a second set of tree branches. Okay. So what will the probabilities on these tree branches be? They're all 0.5 as well, right? It's still boy, girl. So we're still looking at 0.5 probabilities along of all of our branches. All right, so let's figure out what happens with having 2 boys. Well, here is my boy-boy outcome. And if I multiply it, what do I get? Somebody be bold. Thank you. Yes, 0.25. If you're thinking in fractions, this is the number 1/4. Let me just do it this way, or 1/4. So why is it 1/4 and not 1/3? What happened? We said he was right. There's only 3 outcomes. 2 boys, 2 girls, or 1 of each.
Is there like another option from starting with a boy to a girl and then starting with a girl to a boy? Like
Yeah.
it's technically another branch.
You're exactly right. There are 2 different ways that you could get a boy and a girl. And the order matters, right? I mean, like it changes the dynamics in the household for one, but it just changes that there's another outcome that's sort of hidden because we weren't looking at kind of the order of the birth in some sense. So as we're taking a look at this, we want to let Joe know that Joe is incorrect. And there's lots of things you could say, but I think we're going to point out that there are 4 ways of getting 2 children. Getting 2 children, that sounds funny, but we'll go with it. Of having 2 children. And we can look at it from each of the individual numbers here. Like I could calculate that each of these branches is 1/4. That's fine. We could also kind of list it as though we can have a boy, boy, a girl, girl, or we can have boy, girl, or girl, boy, like this, if you want to list it like that. So the probability of having boy, boy is actually 1/4 because there are actually 4 outcomes. Or you can talk about it along the tree branches. You know, they're 1/2 times 1/2 is 1/4. That's fine as well. Okay. Ready for the last example? It's kind of a long one. So this is personal story time. Okay. It fits really well here, and I do this every semester. There's a genetic disease that runs in my family, and it's called Huntington's disease. Has anybody heard of that before? Huntington's disease is a very debilitating disease. My grandmother had Huntington's disease. She passed away. She started getting really ill before I kind of even really remember her very much. She passed away when my now 20-year-old daughter was just underneath 1 year of age. My dad also had Huntington's disease. My dad died 10 years ago. He was younger than his mother for a variety of reasons. His symptoms showed up similarly to when my grandmother's did, which was in their 40s. And it's genetic, which means that you can pass it along to somebody else, right? You have a child, they could get it. So in 2001 was when my parents decided, they knew in 1995 that my dad had Huntington's. And they didn't tell us as children. So just so you know, in 1995, I was 16 at the time. Okay, so you're not that far removed from 16. So put yourself in your 16-year-old head. And we didn't know that my dad had it or anything like that. A few years later, 2001, they decided that they're going to share this news with the family. They shared it to us we were at Thanksgiving. I was married. My husband and I were living in Kansas at the time when we were home. And so I have these very vivid memories of like exactly where you were when those moments happen. I remember exactly. And so I was married. I've been married for almost 3 years. My sister was married. She'd been married for almost 1 year. And my brother was dating the woman that he eventually ended up marrying as well. They were in high school at the time. And so they had a big family meeting. It included, I can't remember if my brother's girlfriend at the time, I don't know if she was there. She might not have been. Everybody else was there. And they told us this information. Hey, so your dad has this disease. And there's a 50% chance that each one of you has it as well. And if you have it, then there's a chance that you would pass it along to your children. And at that point, my dad had gotten bad enough that everybody knew that something wasn't right. In 2001, he was pretty bad off by then. And so I remember going to my bedroom, first of all, being very upset at my parents that they didn't share the information with my husband and with my brother-in-law before they married myself and my sister. I felt like that was not fair to them. I felt like I knew my husband well enough to know that he wouldn't have not married me, but I didn't really feel like my parents had the right to make that decision for him. And so my husband and I went to our bedroom at the house at the time that we were staying with my parents, and I ran numbers in my head. I know that just shocks you, right? That I would run numbers in my head in this kind of moment, but I did. And I was terrified about what that would look like because I saw how it affected my grandfather because of my grandmother, right? Like he had to take care of her. And I knew how it was going to affect and continue to affect my father, and I didn't want that for my kids. And so what we're going to look at next is a tree diagram of the equivalent mathematical process that I went through in my head that day at my house, okay? So we have me, I'm the oldest. I'm sure that shocks you as well. There's two choices, right? It's a 50-50 shot. This is genetic. It's on one of the chromosomes of your DNA, every bit as much as you're either male or female at birth. You have it or you don't have it at birth. It just doesn't show up until later in life for most people, okay? So there's two options. You either have it or you don't, and it's 50-50. So I'm going to do fractions on this one. Child number two, is my sister. My sister lives in Bethany, and she has the same possibilities that I do, right? She either has it or she doesn't. So I'm going to keep saying have, don't. Third child is my brother. And my brother has options, again, of either having it or he doesn't. And all these branches have a 1/2 probability. Okay, so just stay on this screen with me, but I'll read the next question. The question wants to know, what is the probability that at least one of us has this disease? This is the number I ran in my head that day. Okay, so the probability that at least one of us has this disease is every branch that has one of them that has have along it, or more, right? So that would mean all of these branches up here count, and it would mean this branch right here counts, and this one. And it would also mean this one counts. It's almost every possibility, right? It's almost every possibility. There's an easier way to calculate this. We talked about this last time, right? We don't really want to multiply along all the branches and add them up, which we could do. We'd really just like to not include that last branch. So along this last branch, that last branch, what we're going to be looking at is 1 minus the probability that all don't have it. Okay? Along the last branch. So along that last branch, they're all 1/2s, and there's 3 of them, correct? So we're going to have 1/2 times 1/2 times 1/2. All right, so what happens when we multiply 1/2 times 1/2 times 1/2? Close. 1/8. 1/8. And if we do some fraction simplification, this will give us a 7 out of 8. And just for the reference point, because I want you to feel the number, what is this as a decimal? What is 7 out of 8? Grab a calculator if you want to. I don't care.
0.875.
Almost 90% chance that myself or my brother or my sister has this disease. That's a big number, right? If you got an 87.5 on your test, you'd be pretty pleased with that for the most part, right? 87.5 is not bad. That's terrible in this context, right? I mean, it's terrible. And so right then and there, so 2001, how many years ago is that? 22 years, right? 22 years ago. So I was 22 years old, 23 years old, I guess, 23 years old. And my husband and I decided that if I had this disease, we wouldn't have children. Absolutely, without a doubt. We would not be having children. And my mom didn't appreciate that. And I understand why. Because her statement was, if we had made that decision, we wouldn't have had you and your sister and your brother, which is true. But our perspective was looking forward is different than looking back. And God can bring anything out of bad circumstances. But if we knowingly enter something, we're making that choice differently. And so this was the point when my husband and I said, if we have this disease in our family, we're not having children, but we're going to adopt. And that was the first time that adoption was really put on the heart of both of us. I had grown up thinking this would be really cool kind of thing, you know. But he and I had never really discussed it. And so we had decided that we would adopt if in fact, I had this disease. So 2 years later, 2003, happened to be at Thanksgiving as well, oddly enough, was when I got my test results back. We waited a couple years. Genetic testing is not a simple matter. It's not just easy to go in and get it done, especially wasn't then. It's easier now, but it wasn't that easy then. And so you have to go through psychological testing because they want to make sure that you're not going to go and commit suicide, honestly, if you get results. Or they want to make sure that you understand the gravity of it if you're married, right? Like, what if your husband leaves you because of this? It's not a simple question to just be like, blatantly, no problem. So there's a lot of testing of different avenues that you go through or whatever. So 2 years later in 2003, I was tested and I don't have Huntington's disease. But God used that 2-year time span to make it very clear to us that no matter how that outcome was, we were going to adopt. So because I don't have Huntington's disease, we have Abby, my one biological daughter, the one that lives in Kansas. But because of all of the things that God led us through, we have 6 adopted children, which is pretty incredible. And I have to think that my dad, especially, because I knew him well, or I didn't know my grandma that well, but I knew my dad. I have to think that he thinks that's pretty cool. Because how could he not? So we're going to take a look at one more question. I'm going to give you one more piece of information that's happened recently. In 2003, I was tested. I don't have it. So we're going to take a look at what's the probability, given that information, that at least one of my siblings still has Huntington's disease. So we have only 2 branches then, right? Only my sister and my brother. And they either have it or they don't. Whoops, wrong symbol. We'll use decimals now. Feel free to use fractions if you want. All right, so we're gonna do the same thing that we had done again. We're gonna take just this last branch because this last branch is the only one where nobody has it, right? And we're gonna find that probability. So now it's 1 minus the 0.5 times the 0.5. And if you take 0.5 times 0.5, what do you get? 0.25. And if I subtract now, what do I have? 7.5. It went down. That makes sense, right? But it doesn't go down a whole lot. 0.75 chance that at least one of my siblings still has it. So when I taught this unit last spring, my brother was actually in the middle of being tested for Huntington's disease. He had a really scary brain thing happen, and they didn't know what was causing it. It wasn't Huntington's, and like everybody who knew how Huntington's worked knew that that wasn't what was going on, but they decided it was time to go ahead and rule it out anyway. And so he was tested a few months ago, and he doesn't have it either, which is a huge relief. My sister has never been tested. My sister has 3 children, which means they're all at risk as well, and they're all you guys' age. My nephew is 21, my niece is 20, about to be 20, and I have a nephew who's a senior in high school right now, and all of them would be considered at risk because she doesn't know. All right, so I'm going to stop the video.